Hi, this is Gary Millett. This is ELE 110, Electronics for Technicians 1, the fall of 2022. And this is topic number 14, titled Active Devices, or in other words, electronics. So let's get to it. So if we look at the very early history of electricity and electronics, we would say that the electrical era commenced in the early 1800s with the advent of the telegraph. That was really the first application of using electricity to communicate. At that time, there were no electronic components as we know them today. There were, however, batteries, switches, and electromagnetic activated sounders. Sometimes they were called clappers back in the early days of the telegraph. These were all the parts that one needed to create a telegraph, or at least the American version of the telegraph. There were other telegraphs that were invented around the world that used different type of technology. So it would not be until the very early 1900s that vacuum tubes were invented, and not until the middle of the 1900s that transistors were invented. Now, you might say that the first current amplifiers were electrical relays. Relays were invented in the 1830s. There were several different inventors that were credited with building the first electrical relays. The first application was in telegraph systems to extend the reach of the system by relaying the dots and dashes. So instead of a clapper or sounder being read or listened to by the telegraph operator, the telegraph would terminate on a relay, and that relay would extend the reach of the system by having additional miles of wire attached to it to transmit the signal to the next sounder or receiving site. So the traditional electromagnetic relay works by the activation of electromagnetic field, the passing of a current through a coil of wire to produce a magnetic field, which is also known as an electromagnet. The magnetic field in turn causes electrical contacts to either open or close to affect the flow of current through the contacts. So here's a larger diagram of a relay, and you notice we have an energizing coil. There's a armature that's mounted on a pivot. There are movable contacts, there are fixed contacts, and an air gap between the armature and the energizing coil. So you notice there's a coil supply voltage, the blue wire, so a small coil current can switch a large contact current. So you put a small current, let's just use a value like a couple milliamps of current through the energizing coil, which might be thousands of turns of wire, and it'll create a large magnetic field, and it'll cause the yoke, as it's called there on the diagram, to take and be attracted to the energizing coil, the core of the energizing coil. Since the armature is on a pivot, that will cause the movable contact to move up, and the normally closed contact, you notice there's normally open, a common, normally closed. So when it's not activated, the normally closed contact is making contact. When the armature is activated by the energizing coil, it pushes the contact up, and the normally open contacts become closed, and the normally closed become open. So that's kind of how a relay works. There's many different types and shapes of relays. Today they're electromagnetic and solid state, and they're electronic equipment relays, we call them, and here's a bunch of them shown here in this diagram with the contacts, and you might see that some of the contacts you plug in, others you solder into a board, and so forth. So here's some automotive relays, and they would be under the hood. This is a dual headlamp relay and a Bosch horn relay, and you can see the schematics on the front of those things, and they're mounted under the hood of a car. So what about these automotive relays? Well, an interesting thing is that we tend to use them in cars a lot because we have things that need high power, and switches don't last long if they're used with high power, switching high power. So here you see a 12-volt battery. There's a fuse, a switch, and what happens is The lights, which are low voltage and hence high current, tend to be turned on by the relay as opposed to the switch. Here's a solid-state relay. They utilize active devices. So this solid-state relay uses active devices that is semiconductors to switch very large currents, while the input voltage and current can be quite small. Here's some other types of solid-state relays. The input and output are isolated by these, and in each of the 4 cases shown here, the input is either a direct connection to a voltage source. That's the top left one. Notice that the DC input, when the switch closes, there's a infrared LED, and it's called a solid-state relay, SSR, and there's a photodiode that would detect the infrared light coming from the LED, and that will cause the output to close. That's the top left. The top right is a switching transistor. We haven't talked about transistors yet, but if I put a voltage on the input to that NPN transistor, and the input is the line that's going off to the left there, comes in perpendicular to the line that's vertical. If I apply a voltage to that, I'll cause the transistor to conduct. That'll cause the infrared LED to put out a signal, which will cause the photodiode to close the output connections. The bottom left is a logic gate. It's a TTL, stands for transistor logic. And if I take and I cause both of those inputs to go high on that TTL logic gate, it's an AND gate. What will happen is it'll cause the infrared LED to, again, emit energy and cause the photodiode to close the output connection for that relay, solid-state relay. The bottom right-hand one shows a microcontroller, where the microcontroller, if I have the correct inputs to it and running a program, it looks like connection D1 will go low. That will activate the infrared LED and cause the output to close. So all these things are used to interface the device to signals that cannot supply a large amount of current to the relay. This slide is titled the 3 C's, or C3, or C cubed. Communications, command, and control is known as C3 or C cubed, and these terms and abbreviations are quite well known by the military industrial complex because they're used for military armaments and equipment. For our discussions here, let's use another set of 3 terms: communications, control, and computing or computation. So these are the 3 major areas that use electronics to perform the functions indicated by the technology field name. Active electronic devices are used to construct systems that implement useful functions in these 3 areas. Again, if we go back to the last slide, we would talk about command, control, and computing. Communications, maybe. So this slide shows the first active devices. They were vacuum tubes. And the figure on the left-hand side shows you a vacuum tube, a glass tube that's been evacuated. There's a center cathode, which is negative. It gets heated by a filament. There's a control grid surrounding that cathode, and there's another piece of metal in a cylindrical form that surrounds the cathode. It's called an anode. And so in a vacuum tube amplifier, the flow of current within the vacuum tube can be controlled by a grid element placed between the cathode and the plate, or cathode and anode. This arrangement can provide a circuit gain, that is a small input signal yielding a larger output signal. And the picture of that is over to the right. The schematic diagram shows the vacuum tube. This is a triode vacuum tube. There's a large positive voltage V sub A applied to the anode through a plate resistor or anode resistor called R sub A. There's a coupling capacitor for the output to block the DC voltage. There's a cathode resistor, R sub K, and there's a small voltage placed on the grid. And you see that the output voltage on the plate is much higher. Usually a vacuum tube triode would have a gain of about 20, a factor of about 20. So here's a diagram of a flow of current in a vacuum tube. And this is a diode vacuum tube. So it shows the heated cathode, gives off electrons. They are able, because of the heat, to take off into the vacuum that's in the glass enclosure. There's a thing called an anode, and there's a big battery with positive voltage attached to the anode. What happens? That positive voltage attracts the electrons. They go through the space between, the vacuum between the anode and the cathode, and a current flows. So here's a diagram of a flow of current in a vacuum tube that has control grids. And you see that there's a cathode, a grid, and what's called a screen. That would be a tetrode vacuum tube. And it shows the electrons, and what happens is the voltages I apply to the grid or the screen will affect the flow of current for this vacuum tube. So one of the first computers called ENIAC, which stood for Electronic Numerical Integrating and Calculating Machine, was built with vacuum tubes, and you can see the racks of equipment there. These vacuum tubes acted as switches or logic circuits and storage or memory units. Here's another picture of the ENIAC and the vacuum tube components, and replacing a bad tube meant checking among ENIAC's 19,000 possible vacuum tubes. That doesn't sound like a very good job to have. Actually, what they would do is they would burn in, that is, cause the vacuum tubes to be tested first, because vacuum tubes tend to be, as all electronic components, they have what they call a bathtub failure curve. That is an infant mortality and an old age mortality. So computers were first built with vacuum tubes acting as switches, and in this case the vacuum tube either conducted a current, the control grid was not activated or was in the on state, or it did not conduct a current, the control grid was activated, made so highly negative that no electrons could make it to the plate terminal, and it was therefore in the off state. The vacuum tubes could be used in circuits that stored a 0 or a 1, off or on, high or low voltage, which would be memory on our registers, or used in circuits that form logic gates, which were used to perform computational functions. Logic gates take inputs and give certain outputs for certain combinations of inputs. We'll probably take a look at that again later on. So let's fast forward to the present and discuss solid-state devices. So the first device we want to look at is the diode. This two-terminal device only allows a flow of current in one direction. So we have this nice diagram here with the orange P-type material, and N-type material is greenish, and there's a depletion region between them. We take and we manufacture this, so we make a PN junction, and when we make that junction, this depletion region, which is purple in this diagram, forms, and it's neither P nor N-type material. It's a transition between the two types of materials. So the type of semiconductor material, either N or P-type, is determined by what's called the doping process. You can see the, again, graphical picture of what this thing looks like. If you look at part B of the figure, that's the schematic symbol. The P-type material is called the anode, and the N-type material is called the cathode. And if we actually look at a real component appearance, there's a stripe that marks the cathode on the little device. It looks like a resistor, but it has no color code other than that single stripe. So what about the, the doping here? Well, this is a picture of the periodic table of elements, and you might recall that silicon in column 4A is one of the first semiconductors. So what happens is if we add 3A materials, the materials that are in column 3A there, which are boron and so forth down below it, if we add that to silicon, that will yield a P-type of silicon. 5A materials, which start with nitrogen and a gas, we don't use that, but phosphorus, for instance, if we add that to silicon, we yield an N-type material, silicon material. So the 5A column add an extra electron, the 3A column kind of take away an electron, you're missing an electron, and again that yields the P-type and the N-type semiconductor. And silicon by itself, it doesn't conduct very well at all if it's pure silicon. If we dope these things, it turns out they become semiconductors. So here's a diode, and it's shown as a forward bias diode, and a forward bias diode acts like a closed switch. So if I take and put a potential as shown there, plus on the P region and minus on the N region, what happens is this diode will conduct. So the schematic to the right shows a picture of this, and again, plus on the arrowhead and minus on the, the line there, form a forward bias diode, and I'll get maximum current through that diode. And the current here is restricted by the resistor R to limit it so it doesn't burn the diode out. Down below we see the forward bias diode, and it looks like a closed switch. On the next slide here, we'll hopefully see an open switch. Indeed, that's exactly what we see. Here we have a reverse bias diode. This acts like an open switch. So now what happens is if I put plus on the N region and negative or minus on the P region, the depletion area or layer gets wider, and it turns out it won't conduct any electricity. The schematic to the right shows what's happened here, the plus on the stripe of the diode and the minus on the triangle portion of the diode is reverse bias, and the current is equal to 0. And down below you see the biasing of the diode to reverse bias it, and the fact that it looks like an open switch. So here's what a typical diode looks like. There's certainly a blown up picture of one. There are 2 leads. It looks like a resistor to some extent. And again, there's a stripe on one end. And to the right of that is a bridge rectifier. There's 4 diodes in that single package. And you can see on the outside of that package, I put AC on the 2 inner leads, and I take and get plus and minus on the 2 outer leads. So diode applications are many. Here's a rectification, a power supply block diagram. And if you take a look at the top portion of that block diagram, you see AC input, a sine wave. It goes to a transformer to adjust the voltage level, make it either bigger or smaller, or maybe just isolating the primary from the secondary, be the same voltage. The rectifier is the diodes, and the rectifier converts the AC to DC. You see now a pulsating DC output. A filter will remove the voltage pulsations to some extent. You still have a few little ripples there, and then an electronic voltage regulator usually is used to make the DC output very steady. So that's a classic rectifier-based power supply. The schematic is shown on the left-hand side, down below on the left-hand side, and here you see the AC signal is applied. Remember our bridge rectifier, the AC signal is applied to the AC inputs, and the plus and minus are taken off, and there's a smoothing capacitor, we call it a filter capacitor, and a load. This resultant output waveform is shown down below, where you see the dotted lines are the pulsing DC. The capacitor will take and charge up and then discharge in between pulses, and you'll get a waveform that has a ripple on it. So today, and interesting enough, a different technology is used. We use what are called switch mode power supplies, and they're much more efficient using what's called pulse width modulation. But that's for another conversation. What about other diodes? Well, here's the very familiar LED, and you notice that the LED has a plus and minus designation. LEDs will always have one longer lead, that's the plus lead, and the minus lead's a shorter one. Everyone's familiar with a common LED is a red one. This diode device emits light when forward biased, and of course the color of the light depends upon the material used to construct the diode. So here you see the schematic down below, and it shows light coming off from that, and of course if I put plus on the anode and minus on the cathode, what happens is I forward biased this LED to make it emit light. Here's a LED wiring with a breadboard, and you can see how the plus 9-volt battery there. I have a resistor. The resistor is used to take and do what? It limits the amount of current through the LED so it doesn't burn out. Other LED colors. Now, this is a very colorful slide. You see the periodic table. Color emitted depends upon the material used to construct the LED. So here you see red, yellow, green. There's a blue. Blue was the hardest to come by. It took a long time before scientists could figure out the materials processing to make blue LEDs. And the last one on the far left is a white. So if you take the primary colors and combine them, basically have 3 LEDs in there, what will happen is it'll put out a white signal. These are called neopixels, very common today for people to experiment with and make, say, even jewelry out of. Here's a neopixel matrix, and you might notice that it's using a some type of Arduino, it looks like, or Netdino little board there to be powered. And actually you can take and make these things look like color organs. That is, you play music and the light will change and dance around. Here's an 8x8x8 LED cube using an Arduino to power it, and these things are quite cool because you can make the light dance inside that cube and possibly change colors at the same time as changing intensity. Other diode types. There are many other types of diodes. Many of these diode devices has different electrical characteristics due to what? Different doping profiles created during manufacturing. So I'm not going to talk about all of them right now because you might never come in contact with all of them. There's a signal diode. Zener diodes are used for references for power supplies. Tunnel diodes can oscillate or detect signals. There are gun diodes, which will oscillate. Crystal diode, varactor diodes act as capacitors. There's light emitting diodes we've talked about, a constant current diode. There are infrared LEDs, Schottky diodes, pin diodes, avalanche diodes, Schottky diode there in the center, photodiodes, step recovery diodes, transient voltage suppression diodes, super barrier diodes, point contact diodes, vacuum diodes, Peltier diodes, I don't even know what that is in the far bottom right hand corner, silicon control rectifier diodes, laser diodes, and so forth. So all kinds of types of diodes. Now here's a couple automotive applications since we talked about that earlier. This is called a flyback diode, and why we need that is if we have a relay and it turns out that we maybe make the relay close by virtue of being powered by a transistor that gets turned on. When the transistor turns off, the magnetic field of the relay will collapse very rapidly, and actually what happens is a voltage is induced which is reverse polarity of what the voltage was originally, and that can cause the transistor to take and get zapped. So a flyback diode is used to protect active devices used as switches. When the relay activation voltage is removed, the magnetic field collapses suddenly, which induces a very high voltage. The diode becomes forward biased. When the relay is being activated, the diode acts as its reverse bias, hence an open. But when the when the relay gets switched off, what happens is the diode now becomes forward biased and dissipates the high voltage by giving the current a path other than through the semiconductor device. So we have these, if you opened up any hood of any car and you had relays, you'd discover flyback diodes are in place across those relays. Again, here's another flyback, and this shows a fuel pump. So it shows a real-world application of flyback diode. Without the diode, the semiconductor device that supplies the voltage to activate the relay would most likely be burned out by the large voltage created by the collapsing magnetic field of the relay. So this one is a fuel pump, and it gets fired. You see the connector up above, a wire connector EC36, and the blue wire that comes off of that activates the relay for the fuel pump, and it turns out that there's a 10 amp fuse there, so that's quite a bit of current that's in that, creating that magnetic field. And what happens is when it collapses, the diode becomes forward biased and dissipates any of the voltage that's produced by the collapsing magnetic field. So let's move on to transistors or solid state vacuum tube replacements. And just as solid state diodes replace diode vacuum tubes, transistors replace the vast majority of triode vacuum tubes. There are several types of transistor families. There are BJTs, which are bipolar junction transistors, and FETs are field effect transistors, and there are subtypes of these two different families. So you see the diagram there shows like a three-layer sandwich of PNP or NPN, and there are terms collector, base, and emitter for both of those. And it turns out there's two schematic symbols, a PNP transistor in the bottom left, and with a base, collector, and emitter shown. And the emitter is the one who has an arrow on it. Then there's the NPN transistor to the right of that with a base, collector, and emitter. But now the arrow is pointing in. Some people remember NPNs by not pointing in for the arrow on the emitter. If I put a plus voltage on the PNP base, it doesn't turn on. I have to put a negative voltage on it. If I put a plus voltage on the base of the NPN transistor, it will turn on. And by turning on, we mean it conducts from collector to emitter. So bipolar junction transistors are made up of a sandwich of materials. Either NPN or PNP structures yield a bipolar junction transistor, or BJT. How about junction field effect transistors? I have the quote here, think water hose. Well, if you take a look there, one version of our particular version of a field effect transistor, that is a junction field effect transistor, is constructed is shown here. Note the two versions. The far left is a P-type with a channel that is green, and the far right is a N-type with a channel that is gray. So to understand how it works, think about a water hose. One squeezes the hose to cut off the flow of water. The terms for the connections to this three-terminal device are the gate and the drain and source. So in the next slide, I'll show more details. So here's a junction field effect transistor. A potential on the gate changes the size of the conduction channel. So for this type of FET, the conduction region can be altered by applying a voltage of the correct polarity to the device's gate, that is the G terminal. Again, like pinching a hose to control the flow of water. And what happens is you see the drain is positive and the source is negative. Electrons will flow from the negative source to the positive drain, kind of like a vacuum tube. But meanwhile, there's a negative voltage on the gate. And the negative voltage on the gate, which is P-type material, will actually take and cause the P-type channel to take and, or the P-type material kind of to expand, and the N channel to reduce. And you can actually put enough negative voltage on the gate to actually cause the N channel to disappear, and that would cut off all conduction for that device. Again, just like taking a water hose and bending it over and cutting off the flow of water. So what is electronics again? It's the control of the flow of electrons. So this device can control the flow of electrons. This is a MOSFET, or metal oxide silicon field effect transistor, and you see a source on the left and a drain on the right, and there's a gate, and the gate is insulated by silicon dioxide, which means it's basically glass, and it turns out that it's a metal gate, but it's not making any electrical connection with the channel. The channel region is all P-type, so the source and the drain are both N-type, but the P-type substrate is a block between them, and from our diode theory, we could figure out that there's no conduction from the source and the drain of this device if I put a battery across the source to the drain. However, if I do something with the gate, different things happen. So for this MOSFET device, a conduction channel can be created in the channel region by applying a positive voltage to the gate. If I apply a positive voltage to the gate, I'll attract any free electrons that are in the P-type substrate, and there will be some. So it turns out a positive voltage will create an N-type channel by attracting free electrons from the P-type material. So this shows MOSFET operation, bias-induced channel. So here the P-type substrate. Now you can see the N-induced channel. And by the way, since there's a silicon dioxide dielectric layer there, there's no current that flows into the gate. You just put a battery on that, as we have plus on it, to induce the N-type channel, and we call this an enhancement MOSFET, and it turns out that current can flow from the source to the drain if we put a battery across it, but no current can flow into that silicon dioxide dielectric layer. So FET transistors and MOSFETs, in this case, are very high impedance input devices. They don't take any current at all to speak of to operate. So what are some of the applications of transistors? Well, we can have an amplifier, and an amplifier may be constructed from semiconductor devices. Here we show an input signal on the far left, a small signal amplifier, then a power amplifier, and that's all operated from a DC power supply. Well, what happens is that DC power is what gets converted to the bigger AC signal. In this case, it drives, it looks like a loudspeaker, and the increased audio power comes from the DC power supply. We're changing DC power to audio power. And the other thing we can use the bipolar junction transistor for, or the FET, is as a switch. So this schematic here shows this transistor. It's an NPN, not pointing in, as we talked about before. They are in the circuit. There's a relay. There's a flywheel. They call it flywheel or flyback diode there across the relay. For this circuit, a positive voltage applied to the bipolar junction transistor device turns it on and thus applies voltage to the relay. So again, we take and we throw that switch to the on position. We have something called R sub B, a base resistor, to limit the amount of current that flows into the base of the transistor, which is I sub B. And what we would discover is that the transistor from the collector to the emitter would act like a short circuit. So that's, you see an IC current there. Beta is the gain of the transistor. Beta is typically might be 100 to 200. There will be a small voltage VCE across the transistor. It won't go to zero entirely. It might go to about 0.2 of a volt or something like that. But effectively what it's doing is taking and grounding the bottom of that relay. And of course the top of the relay you see is connected to VCC. So it'll turn that relay on and cause the load to be activated. And again, the flywheel diode will be when the switch for the transistor turns off. The magnetic field will collapse, inducing a high voltage, which would normally zap the transistor. But in this case, the current will go through the flywheel diode, which is now forward biased. Here's a bipolar junction transistor power transistor. And it says 10 pieces, so that must come from, this picture must have come from an ad from a company that sells these. And you notice that this has a heat sink because these things do dissipate a lot of power. They get hot. Here's a diagram of a power MOSFET switch. So the power MOSFET looks similar to what we had before. We notice that there's a DC motor in this case. We have a voltage VDD, and we have a snubber or clamping network across that motor, because the motor has the same type of difficulty with collapsing magnetic fields. So in this case, we have looks like a field effect transistor. It's a MOSFET, and it looks like an enhanced MOSFET. Notice that between the drain and the source, there are some openings in that diagram, which means there's no channel there. We form the channel by putting a voltage on the gate, the G terminal, and it turns out in this case we have a T-tail logic, a transistor logic gate, and we put a high voltage on both of those input terminals. Since this is a AND gate, the output will go high only when both inputs are high. That high output will go to the gate terminal. It'll cause a channel to be induced in the enhanced MOSFET that's shown there, and it'll cause a short across from drain to source, which will actually cause the motor to run. So that's a power MOSFET switch. And these things, you don't need to supply any current at all to speak of to the gate to cause that device to turn on. And they can switch, numerous amps of current. Power MOSFET, you might say, looks the same as the before, and you're right. They look the same. Notice again the heat sink with a screw hole, so you can take and attach it to a piece of metal or some type of fin type device, a heat sink device. Recall we talked about these before, so again, just showing them to you one more time. These are again solid state relays. So the question might be, what about ICs? Because that's all we hear in the media is IC integrated circuits. Well, ICs got their start in the 1960s. It wasn't long before op amps were introduced. Op amps simplified amplifier design. A simple ratio of 2 resistors sets the gain. No need to design bias circuits. People were terrorized for decades designing bias circuits to make transistors work. There's a lot of rules you have to follow to get a transistor to become an amplifier. These devices here, you supply a plus voltage and a minus voltage, like plus 15, minus 15, or plus 12, minus 12, to pins, say, 7 and 4. You take and you put a signal into, say, pin 2, you ground pin 3, and you take the output off of pin 6, and all you need is 2 other resistors that feed the signal back from pin 6 to pin 2, and the ratio of the 2 resistors sets the gain. That's a 741 op amp that's been around for 50 years, 5 decades. So here's a couple circuits that show the inverting op amp I just talked about. Notice the gain of this is RF over RN, and they work quite well. That's an inverting op amp because the output is 180 degrees out of phase with the input. The input's going in the inverting input minus input. Next to it is a non-inverting op amp. Same 2 resistors dictate what the gain is. The gain is a little bit different this time. It's 1 plus RF over RN. and it's in phase because the input's going into the plus or non-inverting input. Op-amps have many analog applications. Op-amps can be used as amplifiers, filters, oscillators, summing amplifiers, integrators, differentiators, voltage regulators, constant current generators, I to V and V to I converters, and comparators. So here's an op-amp comparator, the last one on our list. And what happens here is I take and I have a reference voltage on the left-hand side. I'll have a reference voltage applied to the reference voltage terminal there, and I'll put an analog input into the VIN. And if VIN is greater than the reference, then the output will become plus VCC. If VIN is less than the reference, the output becomes minus VCC. So we can use a comparator, excuse me, in a classic control system to compare two voltages. What about logic gates? Well, this diagram here doesn't do justice to them, but it turns out that there are some common logic gates. The name here is not, or sometimes we call it an inverter, an AND gate, a NAND gate, an OR gate, a NOR gate, an exclusive OR gate. And their symbols are shown. The NOT or inverter is simply a triangle with a circle on the output, and it turns out whatever I put in comes out inverted. So I put in a 0, it comes out a 1, put in a 1, comes out a 0. But however, that would be some voltage coming in would be flipped over. The AND gate, the truth table shown down below, shows that the only time the output is high is when both inputs are high or 1. The NAND gate is just the opposite. The output is always high unless both inputs are 1. The OR gate, any 1 on any input will have an output of 1. The NOR gate's just the opposite. If both inputs are low, the output's high. Otherwise, the output's always low. And the exclusive OR gate, if the two inputs are different, is the only time the output is 1. Otherwise, the output is 0. So logic gates may be implemented with diodes, transistors, vacuum tubes, relays, any electronic device that can act as a switch. So here's a little more detail. The output of this logic gate, Y, might be the input to an Arduino or Raspberry Pi GPIO pin, which is what? General purpose input-output pin. For this gate, the two conditions must be true. A and B must be high or 1s for the output Y to be true or high or a 1. Here's an OR gate. The output of this logic gate, Y, might be the input to a Arduino Raspberry Pi GPIO pin again. For this gate, either condition, A or B or both, can be high or true or 1 for the input Y to be true or high or 1. The only time the output's not high is when both inputs are 0. So what about logic gates? Well, this is what we call a combinational logic gate circuit. You notice there's a bunch of gates, and the outputs of some gates drive the inputs to other gates and so forth. There are 4 inputs, A, B, C, and D. Those inputs either be high or low or 0 and 1. And the output of this logic circuit, Z, might be the input to an Arduino or Raspberry Pi GPIO pin. Again, for this combinational logic circuit, only certain values of the 16 possible values of logic inputs of A, B, C, D will cause the output to be true or high or a 1. And notice again, there's 4 inputs, so you have 2 to the 4th or 16 possible combinations of 0s and 1s going in to that logic circuit. Today, logic gates are available as FPGAs, which stand for Field Programmable Gate Arrays. A typical FPGA may have tens of thousands of logic gates on board. There are logic blocks, there are programmable interconnects, and I/O blocks, and you can use a computer or a PC to set up those devices. Modern digital circuits are built from CMOS transistors, and a CMOS is a type of MOSFET. Modern ICs use surface mount technology and can have entire systems on board the chip. Just to show you that these are now into automobiles, here's an application for an automobile, a hybrid power electronics module. Notice the orange color because that's what we use for electric cars now to indicate high voltage. A high power electronics module for an automobile will be constructed for that harsh environment that vehicles are exposed to. And notice you could probably, drop that off the Empire State Building and it would probably bounce. Brake-by-wire systems, it turns out in the future, you're going to discover If you don't have a car like this, eventually you'll buy one. That shows the braking system for a car, and an ECU is electronic control unit, and it says there's a motor there. So this is that automatic braking, automatic emergency braking, where it turns out that if your attention is diverted while you're driving, what will happen is the brakes will automatically take and stop the car for you so you don't get killed. There's a wear sensor wiring on the right-hand side, you might notice. Here's a Bosch DC to DC module for start systems for cars. Another innovation.